Remember that world of grace and beauty and elegance that we talked about in our last presentation? Well, big 180 switch up on you. It's all BS. No one knows what's going on. It's a flaming dumpster fire, like that meme with the dog that says everything's fine, but it's not fine because everything's on fire. As John von Neumann, again, one of my top 10 favorite logicians and mathematicians, said, he said, nobody understands mathematics. You get used to it. Mathematics, he says, is like a fire hose. People are trying to drink from it, but the point is just to get wet. The point is just to immerse yourself in these realities. As Boris Pasternak said, what is laid down, ordered, factual is never enough to embrace the whole truth. Life always spills over the rim of every cup. Any attempt to contain reality itself within a static logical framework will always fail. But mathematics, science, and symbolism of quantity and space, when they know their limits, are the key to unlocking our world's mysteries. It's not about understanding math, it's about understanding how to do math, because math in itself can't be complete and consistent, but mathematics as an enterprise can strive towards greater knowledge and understanding. So, first off, huge respect to you for clicking on this video. I mean, just the motivation and intelligence, again, like I said last time, to not be watching Baby Gronk Riz edits is incredible. I am jealous of you. And that just shows they are so motivated and so prioritizing becoming your best self and self-education over entertainment. So, my promise is that once you're done with this lecture and done with this series, you will understand everything you're taught in math class on a deeper level than your teachers. They'll be like, they'll raise your hand and be like, "Hey, Greg, how do I do math?" And you'll be like, "I got you." So that's my promise. And just quick introduction, I'm Tommy, and CTMU Singularity is where your self-improvement and self-education meets a mindset of absolute truth. I help young guys get so self-actualized that they help start figuring out the meaning of the universe. Subscribe right now so you get this and other similar things on your homepage. If anyone asks you for a source, you have Golden Giga Chad there to guide you. The universe revealed it to me. This is the universe's sign to you. Subscribe right now. And you learn what school won't teach you. I am obsessed with delivering you free value. Join our free school community. Get your free consultation with me, and we will learn and grow together. And that is what I'm passionate about. I've spent the last 3 years obsessing over the most advanced logical and mathematical system in the world called the CTMU. And now I spend all my time teaching other young guys how to conquer the world by becoming the most intelligent, educated, motivated versions of themselves that they can. Without further ado, analytic geometry is where you'll usually start, maybe at a middle school level in mathematics. And it's something that was invented by Rene Descartes, who was a philosopher and mathematician. And he had this idea that we could make a coordinate space to track the movement and position of objects. Very good idea. And that's how we, if you remember those from math classes, mathematical space is usually thought of using a coordinate plane. We are totally locked into this framework. It's a free and empty space with 2 or 3 axes, an x-axis and a y-axis. The 2D coordinate plane has an x-axis, which measures the quantity in one direction, and a y-axis, which measures the quantity in the other direction. A function on this coordinate plane is a relationship between these two variables such that there are never more than 2 y values, such that there's never more than 1 y value for each x value. This is called the vertical line test, because if only 1 y value exists for each x value, then a vertical line cutting through the plane will never pass through 2 points on the function, because it will always just touch 1 or 0. So the line y equals 4x plus 3, as an example, is a line in the coordinate plane with a definite y value for every x value. There can also be discontinuous functions with jumps, breaks, and so forth. Yeah, you can see that right there. There are some examples. These are all functions. They're not super pretty, but they are definitely functions. So basically, there can be discontinuous functions, jumps, breaks, holes, whatever, but as long as they don't have more than 1 x value for each y value, they're good. So x squared plus y squared is an example of an intelligible mathematical expression that is not a function, because it has multiple y values for each x value. So x squared plus y squared equals 16. I'll present that for you right now. If you look at this, it's a familiar shape. It's a circle. It's certainly intelligible, but because it has multiple values for each vertical line that you put through it. For example, here, these two, 0, 4, and 0, -4, that means it's not a function. It's fine. That just describes a circle of radius 4. It's no big deal, but it's not a function. So the study of mathematics using a coordinate system is called analytic geometry, and it's likely what you learned in grade school, even if you don't remember it at all. The problem with analytic geometry is that it represents external relations statically and through the language of mathematical dualism, separating the mathematics from its expression in the real world. So if you're modeling the velocity of a car, you're not taking into account the actual dynamics of that car, you're just taking its position at different times. So a coordinate plane can model the car's trajectory, but it doesn't denote its real world content. It is predictive, but needs to be more expressive. It does not take the reality of the vehicle as its contents, but strips the car of all attributes that can't be expressed in a two-dimensional mathematical space. Just as Descartes, the founder of analytic geometry, separated the mind and physical reality through his Cartesian dualism, he did the same thing here when he separated the content of an abstract space from being able to express anything about the physical universe. Although mind and matter, just as mathematical space and real-world content, can relate in Cartesian theorization, it is not justified how they do so. It just says mind and matter are separate from one another, and there's no way that they can make common contact. And it's implicitly assumed that they're unrelated and can be studied independently of one another. And unsurprisingly, Descartes' philosophy somehow became baked into his mathematics. And this began the situation that we're now in with academic mathematics. Mathematics does not take any physical or metaphysical reality as its content. It's difficult to justify that, for example, non-Riemannian hypersquares have any character of existence outside of the abstract language of mathematical theorizations. Do you see the issue here? When Descartes entered the scene, mathematics separated itself from the real world when it was supposed to take the natural world as its content. So mathematics is the study of quantity and space, which are attributes of the real world. But now mathematics is only studying the quantity and space. And in theory, if you just have the equation, you can get rid of the real world content. That's not going to work if we want to have a true, rigorous theory of mathematics. So mathematics gained much of its current structure through Cartesian analytic geometry, but this came at the steep price of Cartesian dualism. Dualism is now baked into the structure of mathematical theorization itself. It is impossible to have intrinsically meaningful symbols within the current language of mathematics. Geometry is not just, though, the study of functions on graphs like it is in Descartes' analytic geometry, but also involves shape and logic. And that's what it was originally. Geometry means geo for shape and meter, measure, the logic and measure of shapes. This type of geometry is called Euclidean geometry and was invented thousands of years before analytic geometry by a Greek mathematician named Euclid, whose textbook The Elements was the standard for math students for over 2,000 years until the early 1800s. Euclid also forms an integral part of our heritage as a Western civilization, The Elements being translated, published, and studied perhaps more than any book besides the Bible in both the Western and Arab world. Euclidean geometry builds up a study of shapes based on a few axioms, statements, and so forth that are so simple that we can assume them to be true. Euclid has 5 axioms and 5, quote, common notions corresponding to geometric and logical reasoning premises. Note that a line segment a line segment is a portion of a line. What we mean when we say get in a line is actually arrange yourself in a line segment. A line actually extends infinitely both ways. So that's important for axiom 1. Where Euclid says a line can be drawn between any 2 points. A line segment can be drawn between any 2 points that are not in the same location. So you can just draw the line between them. That's pretty clear. You can try this out on your paper, draw 2 points, and then draw a straight line between them. Pretty easy, pretty simple. A line segment can be extended infinitely in the same direction. So in the same way, if you have the same angle, you can just keep drawing forever. There's nothing stopping you. So any line segment is a portion of a line, is basically what that's saying. A circle, which was defined by Euclid, it says anything with a central location and all of the points are the same distance away from the center, that's a circle. So if you have every point filled in, then the distance of any given point to the center is called a radius. So a circle, defined as a geometric construction in which all points are equidistant from the center, can have any center location and any distance that all lines share from the center, called its radius. all right angles formed by two lines that are perpendicular to each other, making a T shape, are equal. For example, the four angles in a square are all right angles. In modern geometric terms, they all have an angle of 90 degrees. So, and then the final one is called the parallel postulate, which is controversial. It's a hot take from Euclid right here. He says, if two lines are pointing towards each other, they will intersect on the lines that they are pointing to. So if two lines are pointing towards each other, then they will intersect on the side to which the lines are pointing. If they are pointing away from each other, then they will intersect on the other side. So here you can see, they cross over because they're both pointing in the same way, and they cross over on the side that they're doing that. If they were pointing the other way, if they were extended out, if there was more than a 180-degree difference between the two angles, then they would meet on the other side. It's pretty simple. And if they are parallel, meaning that they are the same distance away from each other at all values, they will never intersect. So Euclidean geometry is pretty simple. It defines a set of shapes, a line segment, a line, a circle, a point of intersection, etc. He even tells you how to draw them in the book. It's if you read the elements, he's like, oh, okay, well, here's how you draw a circle. You do that, and then you make a bunch of points, and so forth. He doesn't just say circles exist, but demonstrates how to draw one using no more than a compass and an unmarked straight edge. Compare this to modern mathematics like set theory, which just assumes the existence of objects without saying how to create them. Euclidean geometry is the most concrete of the sciences. Euclid also assumed 5 common notions for his reasoning. Things that are equal to the same thing are also equal. For example, if the number of cookies in the cookie jar is the same as the number of pillows on my bed, and there are 3 cookies in the cookie jar, then there are also 3 pillows on my bed. So this is just a definition of the way that we think about number. It's this I don't think is controversial. If equals are added to equals, then the wholes of equals. If there are 2 cookies in the cookie jar and I had 2 more cookies, there will be 4 cookies in the cookie jar. And if I add 2 more pillows to my bed, 4 pillows. For 2 plus 2 equals 4, regardless of what the objects are that we're adding. Since the original number of objects and the number of objects I added were the same, the total number of cookies and pillows I have at the end is the same. This much is clear. If equals are subtracted from equals, then the differences are equals. This is a logical implication of the previous notion, just we're adding negative numbers. So subtraction is the opposite of addition. This is pretty obvious. If I have 4 cookies and 4 pillows, take 2 objects away from each set, I'll be left with 2 cookies and 2 pillows, an equal number of each. Things that coincide with one another are equal. If 2 things are the same, they're the same. This is almost a tautology. For example, if a line segment has the same position at all points as another line segment, they're the same line segment. Simple enough. If 2 things have the same properties, they are the same. This is a little bit philosophically challenging, but for mathematics, it will suffice. I think that's the most controversial one so far, but the whole is greater than the part. So when you add 2 positive integers together, then you get a greater whole than the numbers you added. So when you put things together, they're more than their individuals. It's not that they're more than the sum of their parts, they're more than either of the parts. So that much is clear. So from these simple axioms and notions, Euclid proved everything you might learn in a middle school geometry class. Is that everything you learned there was probably Euclidean geometry. It's probably in a chapter in Euclid's The Elements. So remember all those proofs and things that you had to memorize? Well, you can thank Euclid for that. A well-known example of a result constructed from Euclid's axioms is Thales's theorem, which states that if you draw a straight line across the center of a circle connecting points A and C, then any point B will form a right angle when you draw a triangle between points A, B, and C. So you can see right there, there's a right angle at angle B. In Euclid's Elements, his textbook of geometry, he writes, in a circle, the angle in the semicircle is right, then in a greater segment less than a right angle, and that in a less segment greater than a right angle, further the angle of the greater segment is greater than a right angle, and the angle of the less segment is less than a right angle. So you can see like how logically, how precisely, how mathematically he was thinking about this and writing this down. And this goes all the way back to the Greeks. This is not stated. This is not only stated, but proving using at most the initial 5 axioms and 5 notions discussed herein, and anything derived from them. So he used those 10 simple statements that are totally uncontroversial for the most part, or at least were in his time, and he made everything that we now know about geometry. Absolute genius, one of the all-time greats. So Euclid arranged his hypotheses into a logical system in which each result is proved from axioms and previously proven theorems. Proof is the process of deriving a conclusion from a set of axioms or premises, and it is the essential basis of logic and Euclidean geometry. Geometry is an excellent practice for logical thinking. Yet, the axiomatic method is also provably prohibitive as a general explanation of mathematical structure. Kurt Gödel, the father of modern mathematical logic, proved in his famous incompleteness theorems that a set of axioms can form a complete and consistent model of mathematics. Therefore, within any given axiomatic system, there will always be a disparity between truth and derivability, namely that certain expressions are authentic, they're true, but they can't be proven using a static set of axioms. It's undecidable. So whereas the axiomatic method has been nestled within every region of mathematics and mathematical structure and is now a generic feature of human theorization, Gödel still showed, he said basically that no static set of axioms or inference rules could explain reality or even explain mathematics. So this is a major problem. We're going to run up against the wall if we just try to apply more logic to these questions about reality theory, because logic actually has intrinsic limitations. A quick introduction to mathematical modeling, another topic you might take in a math class, is that generally a model is a simplified version of something else through which you can see whether a theory is valid. If the observations match the model, then you know that the theory corresponds to its universe of reference. A simple example of a model is the heliocentric model of the solar system, which says that the planets revolve around the sun in orbits of concentric ellipses. When the geocentric model of the solar system, that the planets and sun revolve around the Earth, was seen to conflict with cosmological observations, the theory was discarded in favor of a more plausible one in light of the new information. So a good model describes a system in a way that removes most of the attributes and distills them into a few simple variables. I could model our solar system on a computer. It doesn't mean I need to know the position of every single atom and every single planet in that orbits the sun. Is like, no, we just have to know some basic facts. We need to know its mass. We need to know the pull of gravity and so forth. And we can remove most of our attributes, allowing me to predict a complex output based on the input to the model. So this means that models are meant to correspond to their system that they model as best as possible. If in my model I have an asteroid colliding into Mars, then it better have some way that I can predict the effect of that without having to go to Mars and actually perform that experiment, right? So an example of a mathematical model is what I call the linear shirt factory. A mathematical model is a set of mathematical equations corresponding to a system. For example, suppose the total cost of manufacturing 1,000 shirts is $8,500 and the total cost of manufacturing 2,000 shirts is $11,500, and the cost of each shirt is the same. In that case, I'll know that the model of the number of shirts that a factory can create can be given by the linear equation y minus 8,500 equals 3 times x minus 1,000, or y equals 3x plus 5,500. So with this, because I have this linear equation where I can go back to the origin, I can go back to 0, I know for a fact that 5,500 is the initial cost of production, and it costs $3 for every additional unit. So y equals 3x plus 5,500. The plus 5,500 is called the y-intercept because it is when I have a value of x for 0, when y equals 3x plus 5,500. If x equals 0, then y equals 5,500. So it's when the function gets intercepts when the y-axis intercepts the function. So, and then the 3x is called the slope because for every additional for every additional 1 unit that we move forward in x, then it goes up by 3y. So it's a 3-to-1 ratio. That's called the slope. It's like the slope of a mountain. You can imagine yourself, if you can see it on here, just ski down it or something, sled, whatever you do. But yeah. Another example is an exponential shirt factory. This is way better because it gets better over time. In an exponential growth model, the total volume is given by the equation y equals a e to the kt, where y is the total volume of shirts, a is the initial volume, so here it's 1,000, e is a constant roughly equal to 2.718, and k is a positive constant determining the growth rate. T is the length of time that it will take to grow. So here you can see that if y equals 1,000 e to the 0.01t, and it grows at a rate of 0.01 of 0.01, 1% per hour. Then after 69.315 hours, around 3 days, we'll have 2,000 shirts. After 460 hours, less than 3 weeks, we'll have 100,000 shirts. And in less than 20 days, we may have, or in less than 20 days, or less than 40 days, actually, the slide is wrong. But in less than 40 days, we'll have 10 million shirts. In 20 more days. Oh, the slide was right. I spoke it wrong. 20 more days, we'll have 10 million shirts because it keeps compounding on itself. So, no, that's not right. Someone check the math in the comments. When we compare an exponential function like y equals x squared to the linear function y equals 2x, we find that although y equals 2x plus 1,000, the linear function, so-called because it forms a line on the coordinate plane, starts with 1,000 more units than the exponential function, which increases over time at an ever-increasing rate, the linear function is far outpaced in growth by the exponential function. A more complex model on the screen, such as this one, which was the first question on my AP Calc test, might use advanced functions such as integrals and derivative used in calculus to measure change. Still, if you read through this problem and know what it's talking about, all this model is doing is finding the average temperature of a cup of coffee over 12 minutes as it cools. Since this model is exact, it will probably model the temperature of the coffee quite well. Thus, mathematical models help us obtain answers and make very accurate predictions about what will happen in the physical world. Whereas, for instance, tracking the motion of every single molecule in the cup of coffee might be very difficult. It is easy enough for high school students on a timed exam to calculate the temperature of the coffee as it cools in, I think it's around like 15 minutes for the problem. Like, it's not an easy problem, but they can do it since they're given a mathematical model to do so. Yet, dualism remains in effect. This is the big problem with mathematical modeling, is we're separating the modeled space from the system that it is modeling. So the inevitable dualism of the language of Cartesian mathematics between the space in which something is modeled and the objects, properties, and relations that are modeled by the space remain, tending to strip the contents of reality of any attributes that cannot be meaningfully modeled using standard mathematical notation. So in regular mathematics, as we've shown through the examples of analytic geometry, Euclidean geometry, and mathematical modeling, objects, processes, and relations are generated from the bottom up. This means that a mathematical universe of reference is induced from a finite set of axioms and rules of inference. Then this formal system is used to express a mathematical object, process, or relation. This structure will always be distinct from the universe that it models. For instance, no one has ever seen a pure ideal circle that's exactly 3.14159, blah, 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 between the circumference and diameter. It just doesn't exist. There's no actual circle that exists in the world that you can see with your eyes. We just have it as this ideal form. Yet we can describe its properties using mathematics. If I can go, I don't need to go on a little scavenger hunt to find an object with points that are all equidistant from the center, because I can think of one in my mind and I know its properties because of math. So just further, since no set of axioms can be complete and consistent, as shown by Gödel's incompleteness theorem, we probably need something a little bit deeper than the way that we're used to thinking about mathematics. And this is what I'm really excited about, and what I have spent my time learning, is about the CTMU, the cognitive theoretic model of the universe, which is a reality theory that is based on mathematical structure. So instead, in the CTMU, mathematics is induced from the most general algebraic structure called the self-configuring, self-processing language, basically the language of reality, which describes the n-ary identity of reality. Rather than being constructed ectomorphically, looking at objects, properties, and relations through external structures, so looking from without, separating the real universe from its symbolic representations, the CTMU couples these elements into self-dual systems that truthfully reflect the contents of reality while allowing for dynamical structure. Therefore, CTMU mathematics is not static, but is generated through dynamical distributed endomorphisms, meaning it's literally a mapping that happens from the global system to every single point. It's an endomorphism, which means a shape change that happens within itself. So everything is internal to this structure, and the universe is, and the mathematical space is modeled through this distributive process. So this means that mathematics' shape and form are not based on external relations, but rather on internal structure distributed from the primary n-ary or identity, the primitive structure of reality. So CTMU metamathematics is what's needed to dissolve this Cartesian dualism between the universe and math. It does not only take the physical universe, which is technically a linear ectomorphic semi-model, if you care. It's like looking at the universe from the outside and only in terms of the relations and what it's doing in the physical universe as its content, but it takes the structure of reality itself. So therefore, the referent context of CTMU metamathematics is the structure and identity of reality, making it both mathematical in its precision and metaphysical in its content. So this goes well beyond philosophy, because philosophy is usually very imprecise. That's why it's looked down upon by some academics, and mathematics is usually thought of as too lofty. Yes, it is precise, but it doesn't have any real world application. It doesn't connect to anything. There are no non-Riemannian hypersquares. They don't exist. They're fake. They're hoaxes. There's no is this non-Riemannian hypersquare in the room with us? But yes, it is. Because mathematics connects to metaphysics, and so they are needed in a bond of love with one another. You need math and metaphysics to have a structured, orderly view on what existence actually is and how it works. So the current dualistic mathematics languages are not discarded per se in the CTMU, but are instead supported by an embedding mathematical structure. So it is not like saying that anything that we know for a fact, it's not saying we need to remake all the axioms, we need to redraw the coordinate system, get rid of those Descartes and Euclids. They didn't know the CTMU, man. But no, we don't have to do that. We just have to, mathematics as we know it in the CTMU is changed but little in return for what may be vast gains in depth, significance, and explanatory power if fate smiles upon us. Although Langen says in Meta-Religion as the Human Singularity, a 2018 paper that he authored, that once the CTMU is discovered by the academics and recognized for its explanatory power, for mathematics and the hard sciences, it will probably mostly be business as usual, especially at first. This is because in their current forms, both already have places in the CTMU. That is, pure mathematics inhabits SCSPL syntax. So basically, mathematics itself, in the way that even academics who have no idea about the CTMU are thinking about it, it actually fits right in like a square peg in a square hole. It's just they're perfect because the CTMU is a mathematical structure, so it can support this pure mathematics that is generated based on nothing other than logical relationships among these objects. So thus, we do not need to reconstruct mathematics from scratch. We merely need to embed its already existing and extensively developed formalisms into CTMU metamathematics and create a self-dual formulation of mathematics that incorporates the theorist's cognitive syntax and allows its formal structure to be used fruitfully in the referent context of metaphysics. This is what the CTMU brings to bear. It self-dualizes the foundation of mathematics and sets it on firm ground, fertile and well-aerated soil through which it can grow and take hold. The CTMU does not destroy, but fulfills the program of mathematics. Thank you, everyone, so much for tuning in. Let the light shine forth in the darkness. May the peace of our Father in heaven be upon you. Like and subscribe. Peace.